transferred to your row aiming network. And there the A12 algorithm is computed with an input called randf, which means it's a random chosen by the fixed part, by the base station in the row aiming network. And the result of that is a value called res1, which is an answer to an authentication challenge. So when your phone needs to authenticate, then this A11 and A12 computation is done in your home network, in the guest network, and also on your mobile DECT phone. And the random numbers are sent to the DECT phone, and the DECT phone needs to answer with the correct res1 value. And then your DECT phone is authenticated. And also a network can authenticate itself against the phone. In this case, it chooses a value called RS, and your phone, the portable part, chooses a value called randp. And then A21 is computed in your home network, A22 is computed in the guest network. And both algorithms are also computed on the phone. And the phone receives the res2 value from the network and compares it with the value it has generated itself. And if both values matches, then the network is authenticated. So this looks like GSM, with the exception that the network can also authenticate itself. And all this, the complete architecture looks very much like GSM, with the exception that these A algorithms are standardized and they are hardwired into your phone and they are not on a chip card. And what is also supported is encryption using the DECT standard cipher. Can be found here. And when a phone authenticates itself, then there's also a key for the DECT standard cipher generated, which can then be used to encrypt your phone calls. So in theory, DECT security looks nice. UAK is a 128-bit key, which means it's much longer than usually the keys used on GSM. And authentication of the network and authentication of the phone is both supported. And for every conversation, a new key is generated. And you got some parts in your home network. Your keys don't leave your home network. Oops, sorry. Your keys don't leave your home network. And you got some parts which are executed in the guest network. And in theory, this doesn't look so bad. Now the problem is, because all algorithms are hardwired into the phones, the people who created DECT choose to keep their algorithm secret. So these four algorithms, A11, A12, A21, and A22, are called the DECT standard authentication algorithm, and they are a secret to the creators of DECT and all companies which create DECT devices and which build DECT microchips and that. And also the DECT standard cipher, which is used to encrypt your DECT calls. This algorithm is also secret and is not known to the public. And when you create DECT devices, you can choose. You can either use these. You can either go to the ETSI and sign a non-disclosure agreement and get these algorithms and hardwire them into your phones. Then you are compatible. Then you're interoperable with other DECT devices. Or if you want to build a closed DECT system, you can also replace these 5 algorithms with an algorithm of your choice or algorithms of your choice. Then you got still a DECT system, but you cannot be interoperable with other DECT devices. Okay. As I said, in theory it's nice, but sometimes there is no authentication and encryption active at all. And there are some cases where only base stations require authentication of the portable part, which means only your phone must authenticate against the network, but the network does not authenticate against the phone. This is usually the case with GSM, and this also happens very often in DECT networks. And sometimes you have authentication of both devices, but they do not use encryption. And this means you can run trivial attacks with the right hardware. So what we did, we created a universal DECT sniffer. We used this standard PCMCA card to implement such a sniffer. We have written a driver for the Linux operating system. And we have a user space utility which scans for active calls, tracks the first call which is found, records all data in the call, and waits until the call is over or until connection is lost, and then it starts scanning again for the next call. And all call data is written down to the disk in PCAP files, and we get a special audio player which can then play these PCAP files. So when you are next to a DEC network and they do not use encryption, and this is the case for a lot of networks in Germany, then you can just fire up these utilities and record every conversation on the network. Currently, the code works. Sound quality is not that good at the moment, but it's okay. And the total costs of this attack tool is €23 just for the card if you have a laptop with a PCMCIA slot and you can install Linux on it. So. Step 2. If encryption is used, this tool does not work. In this case, we decided to impersonate a DEC base station. So as I said, some phones, and with some I mean all phones I could get my hands on so far, they don't require authentication of the network. So what we did, we created a modified driver which acts like a base station, and well, the first thing you do is you scan for base stations in your neighborhood. You get a listing of all RFPIs of all stations, then you choose a specific station you would like to impersonate, you start a script, and then the driver is configured to impersonate exactly this base station. And what happens is then your driver starts broadcasting the same RFPI, and if a phone is switched on near your laptop, which would like to communicate with the original base station, it will automatically log on to your base station if your signal is stronger or your base station is found first or whatever. And the next thing we need to do, we need to register phones on this base station. We need the IPUI of the phone. This is a kind of identification ID of a phone. We get a second script which registers an arbitrary phone with this base station, and we all run that locally. And after that, the phone is logged in onto your base station, and your base station routes out phones via a SIP provider. So you can register this faked base station with an asterisk server, and this asterisk server can then reroute calls, record calls, whatever. And phones don't require encryption. And so we don't need to know any secret for that. We don't need to break keys. We can just, we can just require authentication of the phone. The phone authenticates, sends us this res value back, and we just accept it, and we don't say anything, and we say that we don't support encryption, and then the phone starts the call without encryption, and we don't need keys for that. So this is a very nice attack tool, and total cost is €23 again for the card, and then you can at least attack every DEC system we have seen so far in Germany. We only had a look at perhaps 5 to 10 phones or so, but they all worked with this impersonated base station. So in this case, we can even attack systems where encryption is active but not enforced, and this should be nearly every DEC system in Germany. Okay, next step, the DEC standard authentication algorithm. The algorithm is used for authentication of the portable part, which means authentication of the phone. It's used for authentication of the fixed part, which means authentication of the network. It's used to generate the keys for the sessions for the phone calls. So every time you start a new phone call and you use encryption, a new key is generated using the DSA algorithm. And it's also used for generating the UAK for DEC gap devices. So the standard specifies multiple ways how to generate UAK. You can just enter it manually, you can program it into the EEPROM, but if you have DEC gap devices, which are, and all modern DEC devices are DEC gap devices, then the DSA algorithm is also used to generate the initial pairs from a random number and the pin you enter when you pair the phone with your base station. The algorithm is secret, not anymore. we decided to reverse engineer the algorithm. So DSA are 4 algorithms: A11, A12, A21, and A22. And all other algorithms besides A11 are just wrappers around A11, which just cut out a small piece of the output or invert bits of the output or something like this. And A11 is an algorithm which takes a 128-bit key and a 64-bit random number to generate a 128-bit random output. And A11 uses 4 different block ciphers we decided to call Casable because we had a name for these block ciphers to generate the output. This is the structure of A11. So we got these 4 block ciphers. The key always goes in on the left side, and the input goes on from the upper side, and the output comes down on the bottom side. And key is the 128-bit key used as an input for the A11 algorithm, and rand is a random number, which is depending on whether the algorithm is used in the DEC protocol called randf, randp, or RS. And this is the logical structure how the output is generated. Yeah, ref just reverses the byte order of an input. These signs here just means you concatenate your input, and with these brackets, I mean cut out bits 96 to 127 inclusively from the value key. And yeah, this is the A11 algorithm, and we also have a detailed analysis of the Casable block cipher. It's a substitution permutation network. Input is 64-bit, the key is 64 bits, the output is 64-bit, and the internal state also has 64-bit. As a key scheduling function in the block cipher, a bit permutation is used, and each variant of these 4 Casable block ciphers only differs in the bit permutation. And the round key is just added with an XOR to the cipher. And a single invocation of the cipher does 6 rounds in total, and each round consists of the addition of the round key, an application of an S box, which we also know, to the internal state, and then a kind of butterfly mixing. So there are 3 different mixing functions which look like a butterfly network, and which mix each bytes in the states with another byte in the state. And at the end there is no final key addition, which reduces the strength of the cipher to only 5 relevant rounds. We did a little cryptanalysis on the cipher. When you first look at the block cipher, at this Casable cipher, you think that there's full diffusion after 3 rounds, so after half of the rounds. But if you look a little bit more closely, you see that it takes at least 4 rounds after you get full diffusion. Full diffusion means that every bit in the internal state depends on every bit on the input and every bit of the key. And we were able to do some linear cryptanalysis attacks for 2 to 3 rounds version of the cipher. We were able to find an algebraic attack which can break 3 rounds of Casable. And we also have a differential attack on the full cipher, which leads about 16 pairs of inputs and outputs, where you need to choose the inputs. And you can then break the cipher with an effort which is comparable to 2237 invocations of the block cipher. So in theory, you should need 2265 invocations of Casable to break Casable. But with this attack, you can do it with 2237 invocations. This work has been mostly done by Stefan Lux on the differential attack. And however, this has no direct impact on the DECT standard authentication algorithm so far.